Hi, welcome to Lessons 4 of Vectors. Today we're going to look at the vector between 2 points and parallel vectors, but before we do that we need to have a quick look at position vectors. Okay, so what is a position vector? So essentially it's just the column vector that represents the position of a coordinate relative to the origin. So what that means is, what's the column vector to get from the origin to coordinate point A, or the column vector that would represent the journey from the origin to coordinate point B. So let's look at coordinate point A first of all. Okay, so we can see that that has the coordinates 2, 5. So the vector from the origin to the point A, we would have that as OA with the arrow above it. But often we just label this as lowercase a underlined. So if the coordinate point is labelled with the uppercase letter A, then we use the lowercase letter a to represent the vector from the origin to that point. Now we can just see, just like the coordinate, we need to go 2 to the right and 5 up in this case. So we just write this as a column vector. So we write it as 2, 5. So essentially it's just the coordinate written vertically. So it's as easy as that. Let's look at coordinate point B. Okay, so we can see that that has the coordinates 6, 1. So the vector journey from the origin to B, that would be OB, or lowercase b, as we will label it with. And we can see to get from the origin to B, we need to go 6 to the right and 1 up. So our column vector would just be 6, 1. If you pause the video just now and make sure you've copied this information in, and then have a go at the examples on the next slide, please. Okay, so pause this slide for a minute or two and write down the column vectors that represent the positions of each of the coordinates shown on the diagram. Okay, so the first example, we can see the coordinate P is 2, 3. So therefore the vector is OP, or lowercase p underlined, and that would be 2, 3 written vertically. To get from O to Q, we need to go 3 to the right and 1 down. So the vector OQ, or lowercase q underlined, is 3 minus 1. To get from the origin to R, we need to go 2 to the left this time, and then there's no vertical movement, so the vector R underlined is minus 2, 0. Vector S, so going from the origin to point S, we need to go 1 to the left and 2 up, so that would be minus 1, 2. And then lastly, to get to the point T from the origin, the vector lowercase t would be, there's no horizontal movement, just 1 down, so that would be 0, minus 1. Okay, so now we can start looking at the vector between 2 coordinate points. So if we have 2 coordinate points A and B, the vector between them can be found by using a little formula. So the vector from A to B is the column vector of B subtract the column vector of A. So if we have a look at the example we have below, we can see that A is the point 2, 5 and B is the point 6, 1. So without having to plot the points, we can use the formula. So the vector from A to B will be the vector B minus A. Now technically that's negative A add B, but we just tidy that up, and that's where we get the B minus A from. So we can see that the vector B is 6, 1. Subtract the vector A, which is 2, 5. So 6 take away 2 is 4, and 1 take away 5 is negative 4. Now because we have a diagram here, we can actually check that. So we can see to get from A to B, we go 4 to the right and 4 down. So that's represented by a column vector of 4 minus 1. But the whole point of having that little formula is so that we don't need to plot the points every single time we want to do this. We can just use the formula and work it out as a calculation. Second thing to note is, what is the vector BA? If we have found the vector AB, remember the vector BA is just the negative of this. So if the vector AB is 4, negative 4, then the vector BA is negative 4, 4. Remember, we just change the signs of the components to get the negative vector. Let's have a look at the next slide. So here we're going to look at examples where we're not going to plot the coordinate points, we're just going to find the column vectors using the little formula. So we've been given 3 coordinate points, A which is 3, 4, B which is 4, minus 1, and C which is minus 3, 0. And we want to find the column vectors to represent the vector AB, to represent the vector journey BC, and to represent the journey from C to A. So let's look at the first example. So the vector journey A to B is the column vector of B subtract the column vector of A. So that would be 4 minus 1 subtract 3, 4. So we just do 4 subtract 3 at the top, which gives us 1, and minus 1 subtract another 4 is minus 5 at the bottom. So the vector that would represent the journey from A to B is 1 minus 5. Similarly, if we look at the vector journey from B to C, so this time we can alter the formula to represent the coordinates that we're using. So for BC, this time the formula would be C subtract B. So you notice it's always the second letter subtract the first letter. So the column vector of C is minus 3, 0, and we're subtracting B, which is 4 minus 1. So minus 3 subtract 4 is minus 7. And then 0 subtract negative 1, we have a double negative, so that's 0 plus 1, which is positive 1. So the column vector that represents the journey BC is minus 7, 1. Lastly here we have the journey from C to A. So this time the formula would be A subtract C. So we're going to have 3, 4 subtract minus 3, 0. Again, we've got a double negative, so 3 add 3 is 6, and then 4 subtract 0 is just 4. So the column vector to represent the journey from C to A is 6, 4. Right, let's see how well you understood that. So if you can have a go at Vectors Worksheet Exercise 4, please, and complete questions 1 and 2. Check and correct your work from the answers at the end of the sheet, and then come back to the rest of the video. Thanks. The last part of today's lesson is looking at parallel vectors. So for two vectors A and B, A is parallel to B if A is equal to something times B. Now we use K to represent that value, and K can equal 1, or it can be any other number, and we just call that a constant. Now this could be a whole number, or it could be a fraction. So let's have a look at some examples. We've got 5 coordinate points here. So A is the point 2, 5, B is 6, 1, C is minus 1, 4, D is 1, 2, and E is the point 3, 0. The first thing we've been asked to do is show that the vector AB is parallel to the vector CE. In order to do that, we need to get column vectors to represent both AB and CE. So let's begin. So we've got the points A and B. To get the vector AB, we do column vector B subtract the column vector A. So 6, 1 subtract 2, 5, and that gives us 4 minus 4. We do the same for the points C and E. So C is minus 1, 4, and E is 3, 0. So CE is the column vector of E, take away the column vector of C. So we've got 3, 0 subtract minus 1, 4. Double negative gives us a positive, remember, so it's 3 plus 1 is 4 at the top, and then 0 subtract 4 is minus 4 at the bottom. So you notice here that both the vectors are the same. So we would say here that AB is equal to CE, so therefore AB is parallel to CE. So if you notice here, the vectors are equal, so that in this case that means K is equal to 1, because we know if we multiply anything by 1 we just get the same thing. And that also means the vectors are parallel, but they are also the same length. If we have the same vector, then we would have the same length. If we wanted to show that, then we would just use our Pythagoras method to get the magnitude of each vector. Now, if you remember that, because that will come in handy later on when you're working through some examples. Let's look at example B. It's the same 5 points we're working with, and we've been asked to show that vector AB is parallel to vector CD. So exactly the same procedure as before. We need to get the vector AB. So that's column vector B subtract column vector A. So 6, 1, take away the 2, 5, which is the 4 minus 4. We've already worked that out in the previous slide. If we look at vector CD this time, so that's column vector D subtract column vector C. So that will give us 1, 2 subtract minus 1, 4. Double negative gives us a positive, so we end up with 2 at the top and minus 2 at the bottom. So the vector representing CD is 2 minus 2. Now if we compare the two vectors, we can see that AB is double CD. So we would write that as AB equals 2CD. So therefore AB is parallel to CD. We're showing that one vector is a multiple of the other. So AB is parallel to CD. So again, if you just notice here, K is 2. So the vectors are parallel and AB is double the length of CD. Okay, last example, and then you guys can have a go yourselves. So this time we've got the same 5 coordinate points again, and we're being asked, is AC parallel to EB? So it's exactly the same procedure as before. We work out the vector for AC. So this time it's C subtract A. So minus 1, 4, subtract 2, 5, and we get minus 3, minus 1. We do the same for EB. So column vector B subtract column vector E. So 6, 1, subtract 3, 0, and we get 3, 1. So if we compare the vector for AC to the vector for EB, we can see that EB is the negative of AC. So it's the same idea again. Because they are the negative of each other, it's a multiple, so AC is parallel to EB. So just to clarify that, here we can see the value of K is negative 1. So the vectors are parallel, and all it's saying is AC is the negative vector of EB. Remember, the negative vector of EB is actually vector BE then. Okay, let's have a go at you trying some questions. Right, so you're going to have a go at some questions yourself. So if you can go back to the Vectors Worksheet Exercise 4 and complete the rest of the questions 3 to 5, and then check and correct your work. Then once you've done that, if you can use the rest of your double period and complete as many questions as you can on the next part of the worksheet, which is the mixed exercise. Again, just check and correct your work and use the answers at the end of the worksheet, and that is your lesson for today.